Based on this simple set of experiments, based on this simple set of observations that we made with nature, we have a whole new civilization that has begun. So all the life that we have now is based on this simple experiment. So what is that we are looking at? We're looking at a coil, a magnet, and a voltmeter. So we're picking up the magnet, getting it near, pulling it out. So during this time, what is that you have to observe is, as and when it goes near, look at the voltmeter. And when it's stationary, that's there is no movement. Again, we have to look at the voltmeter. When it's moving away, again we have to look at the voltmeter. So I'll play the video. You guys try doing that. Keep observing the voltmeter. Let the hand movement be in the background. Again, I'll just play the last bit. Observe the voltmeter. Let the hand movement be in the background. Okay, so let's try to come to certain conclusion. What is that we're looking at? We are looking at a magnet going near a coil and coming away from it, moving away from it. When it's going near, there is a voltmeter reading which is non-zero, and when we are pulling it away, then too we have a reading. When we are making it go near, we have a negative reading, something like that. When we are pulling away, we have a positive reading. The moving in wala, the value is a bit lesser, actually much lesser than the one when we taking it outward. That's for a reason. That's supposed to be equal, provided we have done the experiment right. And there is quite a few factors, of course. That is what we are looking at the entire chapter. Why is it negative? Why is it positive? Why is it less? Why is it more? All of this question is what we are learning the entire chapter. For now, the thing is, this is the starting point. And this was done by Faraday. So he looked at and he did quite a few variations of this experiment. We are looking at some of them. So it has to do with the cause and effect, which we just saw. We got introduced to the idea of induction, the term, and what does electromagnetic induction look like. These are the few of them. So induction with magnet and coil, induction with two coil, induction without relative motion. So what we looked at was motion. So this two has to do with motion, and the last one is not to do with motion. So how is that we are able to do this without motion? That's what we're trying to learn. So one thing over here is these are only small possibility. There are a lot more variations. Now let's look at the experiments. So the same experiment, whatever we just saw, that's what we're looking at. So the setup is we have a galvanometer. We have a coil. And we have source of magnetic field, a bar magnet. Now, procedure. Move the bar magnet towards the coil and away from the coil. So back and forth. Flip the bar magnet and do the same. And finally, keep the bar magnet stationary, something like this. So you can see this is not a paused video, this is an actual video. You can see there's no voltage. So what is that we'll observe in doing all of this? The galvanometer needle deflects when the magnet is moved and no deflection if it's stationary. So basically, this shows no deflection. Provided this is at rest. Just a second. when there is motion, right, back and forth, then there is a deflection. The deflection depends on the speed and direction of the magnetic motion. If the movement is faster, deflection is more. The direction of the galvanometer needed deflects in relation to the magnet's motion and polarity. So, in what direction is the current? How much is the current? That depends on quite a few factors. That's what it means. Of course, that's what we are learning in the next set of videos. So, whatever is observed in the North Pole, the opposite is observed in the South Pole. If the deflection was to the right with North Pole when we are moving it, the deflection will be to the left when we are moving in with the South Pole. Don't worry, we'll understand that. Next, second experiment. Same coil, but instead of a bar magnet, we have a solenoid. This is a solenoid which is say switched on. What happens over here when you switch it on? Yes, there is a magnetic field. So basically, we have a bar magnet in form of a solenoid. So basically, we have a source of magnetic field. Now, the same thing, instead of bar magnet, we have another source of magnetic field. Same stuff, right? Procedure is the same. What do you observe? Galvanometer deflects when the second coil is moved. Again, you have to label it. And by the way, each of this experiment can come as a separate question. So depending on the question and depending on the marks, you guys have to take up the details. Don't write the setup if not needed. You pretty much have to write the procedure and observation in every form of question. So again, depending on the question, again I repeat, depending on the question, you guys write whichever experiment is asked for, how much ever experiment is asked for. So the galvanometer needed deflects when the coil are in relative motion, indicating an induced current. The direction of the deflection reverses when the direction of the motion is reversed. Same stuff, same observation. Okay, next. Deflection without relative motion. Now we're not moving it. But even then we can observe this. How is that possible? Right? Let's see this. Two coil, one connected to a battery and another to a galvanometer in this manner. Again, label all of this. So we have this to be your galvanometer. Label end to end. Don't write short form. Say coil 1. Say coil 2. Whatever you write, same convention has to be here as well. So this is your rheostat. Okay. So what is a rheostat? Rheostat is something, it's a resistor basically, whose value can change. So this, I'm sure you guys would have seen it in your labs as well. So what is the stuff? What is that we're looking at? So complete the circuit with push button while the coil is stationary. The coils are stationary. Vary the rheostat and observe the direction of the galvanometer needle deflection. Observe the direction of the galvanometer deflection when the coil is broken. So there are three variations that we have spoken of. Varying the rheostat, it can increase or decrease. Doesn't matter. Okay, we can increase the resistance or decrease the resistance of a rheostat. But here the key thing is, what do we observe? The galvanometer deflects when the circuit is completed and broken. Okay. The galvanometer needle also deflects when the rheostat is varied. So why does this happen? When we change the resistor, right? When you switch on, switch off, the resistance is changing. It's moving from 0 to infinity and in between. So what happens? The current value changes. What happens? Because there is change in current value, there is change in magnetic strength. And so that has been exposed to your second coil. This indicates that a changing magnetic field alone can induce a current even without relative motion between the coil. This is what is important. The induction happens whenever there is a changing magnetic field. Whatever change can be, it can be an increase or decrease. Point is change. The key word here is changing. Okay, yes. So finally, let me conclude over here. All three experiment demonstrates that whenever the magnetic flux linked with the closed circuit changes, an EMF is induced. The direction of the induction is always such as to oppose the change that causes it. This we'll be discussing, don't worry. Higher the rate of change of the magnetic flux linked with a closed circuit, the greater is the induced EMF and current that we have observed in experiment. Okay, so again, keyword here is changing. Simple, that's all. All that we are doing is understanding what is seen in nature and putting it as words and experiments and making use of that. Our lives are so because of this set of observation made and behavior in nature. Okay, now you guys have to write everything.